Hi dear students, today we are going to discuss boundary conditions, the reflection and transmission. Okay, so in the last class, we have discussed in detail about uh, the representation of a wave in complex notation. So suppose if you have a sinusoidal wave, which is propagating in z direction, then it can be represented as f tilde zt, which is equal to a tilde e raised to I kz minus omega t. Okay, and what is this a tilde here? This a tilde basically represent a times e raised to I delta. So a tilde contains both the amplitude and delta represent the phase of the wave. So this is what is called the complex representation. The actual representation would be the real part of this, so which is f of zt. This can be written as some a cos of kz minus omega t plus delta, which is the real part of f tilde of zt. So it is always convenient to use this the complex notation. So in this particular steps, and not only in this particular lecture, in the later lecture also, all the remaining lectures we will be using this complex notations. Okay. So this topic, today's topic is the boundary condition, reflection, transmission. So the situation is this: suppose you have a very long string which has some boundary. Okay, so you have combination of two strings. One is a lighter string, which is having some linear mass density mu1, and another one is a thicker string with some linear mass density mu2. And we have some boundary here. And boundary I am going to denote by symbol z is equal to 0. Okay, suppose if you produce some wave here, so you can produce a wave by just oscillating one end. So if you produce a wave here, this would propagate towards the direction. So this is your z direction. Okay, and it will propagate along the z direction. Now when it reaches this boundary at z equal to 0, what would happen is some portion of this wave would get reflected, some portion of the wave would get reflected, and some portion of the wave would get transmitted. Okay, so by using these boundary conditions, we can actually find out how much the energy is transmitted, or how much the amplitude is get transmitted, and how much energy is get reflected, or the what is the amplitude of the reflected wave and what is the amplitude of the transmitted wave can be found out by using the boundary condition. Okay, now what is the boundary condition here? So in order to find out the boundary condition in this case, first we have to recall the wave equation. So we know that if f tilde is a wave function, suppose this f tilde of zt represent the wave function. Now this wave function has to satisfy the wave equation. And what is this wave equation? So the wave equation is given by dou square f tilde by dou z square is equal to 1 by v square dou square f tilde by dou t square. So this is the wave equation in one dimension. Okay, so here we are considering only one dimension. The wave is propagating along the direction. Wave equation in one dimension. Okay, now this wave equation, if you look at this wave equation is a second order equation. It is second order differential equation in space z and time t. So in order to get the second order, or in order to define the second order differentiation for a function, its first order its first order derivative and as well as the function itself must be continuous. Okay, so that is the mathematical theorem. So in order to find the second derivative of f tilde of zt with respect to z, so that means you have to find dou square f tilde by dou z square, this function f tilde of zt, and dou f tilde by dou z must be continuous. Okay, so it must be continuous at all points. At all points z. So that means it must be continuous even at z equal to 0. That is even at the boundary. So this would be the boundary condition that I am going to use here. That is this f tilde of zt and as well as dou f tilde by dou z must be continuous. So this is a condition that I am going to use. Okay. Now we can write this f tilde explicitly. So I have not written the f tilde. What is the functional form of f tilde here? So if you look at f tilde, we can divide the string into two parts. One is the left part of the z equal to 0 and right part of the z equal to 0, because uh, at the both sides of the boundary we have two different strings which is having different the linear mass density. So correspondingly the speed of the wave would also be different. So the speed of the wave we can write here is v1 and here it would be v2, and for massive string the speed would be lesser. So if the mu2, if mu2 is greater than mu1, if mu2 is greater than mu1, okay, so that is possible because if you look at the right side of the boundary, the string is a little thicker, so obviously the mass density would be higher there, so m2 would be greater there. So if m2 is greater than mu2 is greater than mu1, which implies v2 would be less than v1. Okay, so first of all, we can find out what are the waves at the boundary z equal to 0, the left side of z equal to 0 and right side of z equal to 0. So at left side, it is for the region z less than 0, the f tilde of zt, it has two waves now. So it has the incident wave which is moving towards right, and it also have a reflected wave. So for z less than 0, we have two waves, the incident wave and reflected wave. The incident wave we can represent by symbol Fi, and reflected wave we can represent by symbol Fr. So Fi tilde and Fr tilde. So F tilde of Zt we can write Fi tilde of Zt plus Fr tilde of Zt. It is for Z less than 0. It is on the left side. And what about the right side, Z greater than 0, the wave F tilde of Zt. So on the right side, we'll have only one wave. We have only the transmitted wave. Okay, so transmitted wave, we can write ft tilde of zt. Okay, so this is the explicit form of f tilde. Okay, now we can write down the each of these wave fi, fr, and ft, so that you can easily write down, because fi tilde of zt, if you look at fi tilde of zt, this incident wave is propagating towards positive z direction. So the right towards right is your positive z, is your positive z, towards right is positive z. So the incident wave is moving in positive z direction. The transmitted wave is also moving in positive z direction, whereas the reflected wave is moving in negative z direction. So accordingly, we can write the complex form of these three waves. So fi tilde of zt, we can write ai tilde, the complex amplitude of the incident wave, times e raised to I k1z minus omega t. And what is ai tilde here? Ai tilde is the amplitude of the incident, the real amplitude of the incident, plus e raised to I delta I. Delta I is the phase of the incident wave. And Fr, the reflected wave, we can write its amplitude as AR tilde and e raised to I. It is moving in negative z direction, so we can write minus k1z minus omega t. So since the reflected wave is in the same string of the incident wave, there will not be any change in the wavelength. So the wavelength would be the same. So or the wave vector would be the same. So that is why I've written k1 in both cases for the incident and reflected. But the direction is different. So that is why I put an additional negative sign here. Okay. So finally, the transmitted wave. The transmitted wave is propagating in positive z direction, and its amplitude I can denote by symbol at tilde e raised to I. So obviously it should have a different wavelength, so a different wave vector. So k2 z minus omega t. Now recall the your one point. So in the case of propagation of wave in a string, the speed is decided by the linear mass density. The speed of the wave v is found to be square root of T by mu, where T is the tension in the string and mu is the mass per unit length. The speed is decided by the string. What about the frequency? The frequency of the wave decided by the source. Okay. So in order to produce the wave, there should be some source. It may be a machine or it may be a person. Okay, so there should be some source which oscillates the wave, which oscillates the free end of the which oscillates the free end of the string. Okay, so that source decides the frequency of the wave, because what is the wave frequency? The frequency is the number of wave produced per second or number of wave produced in unit time. So remember, the frequency is number of waves produced in unit time. So this frequency is connected with the source. There is no role for medium, there is no role for the string to decide the frequency. So the frequency is entirely decided by the source. So whether the wave is moving in a single string, or whether the wave is the transmitting from the one string to the other string, its frequency will remain unchanged. The frequency will remain unchanged. But what would change there? The speed of the wave would change. And we know that for any wave, the speed is connected with the frequency and wavelength according to this relation. The speed equal to the frequency multiplied by the wavelength. And the frequency is always same during the propagation, because frequency is decided by the source. But the speed is depending upon the medium. In case of the string, the tension and as well as the mass per unit length decides the speed. So therefore, the speed changes when the wave moves from the one medium to the other, or when the wave moves from one string to the other, but the frequency remains same. So correspondingly, there will be change in wavelength. Okay. So that is why in this entire expression, I have not changed I have not given any subscript for the frequency omega. So if you look at the incident wave, the reflected wave and transmitted wave, the frequency remains same. It is the omega throughout, but the wave vector is different. Okay, for the first string, the wave vector is denoted by symbol k1. For the second string, the wave vector denoted by the symbol k2. Okay, so that is the explanation that is required. Okay, now therefore we can have this relation. So we know that the speed of the wave in the first string v1, better we can use some other color. So the speed of the wave in the first string can be written as f times lambda 1, and the speed of the wave in the second string is f times lambda 2. So if you take the ratio between these two, v1 by v2, that is simply equal to lambda 1 by lambda 2. Now, what is the relation between the wavelength and the wave vector? So k1 is 2 pi by lambda 1. So the wave vector and wavelength are inversely proportional. So therefore, v1 by v2 is also equal to k2 by k1. Okay, so this relation may be required in future. In the remaining steps we required. So that is why just keep this relation in your mind. Okay, so now we have two equations. The complex wave function on the left side of the boundary, and the wave function on the right side of the boundary. So this is our the wave, the expression for the wave, and this is the main equation that we require. So this we can represent by the equation number 2, and this is our original equation, equation number 1, and these three equations we can write equation number 3, 4, and 5. Okay, so we can write our the expression for, or the complex wave function f tilde of zt in this way is equal to ai tilde e raised to I k1z minus omega t plus ar tilde e raised to I minus k1z minus omega t. It is for z less than 0, and it is equal to at tilde e raised to I k2z minus omega t for z greater than 0. So this would be a wave function. Now this wave function, this complex wave function must be continuous at the boundary, and as well as its first derivative should also be continuous at the boundary. So that means f tilde of zt from the limit z tend to 0 minus would be equal to limit z tend to 0 plus f tilde of zt. So if you are approaching from the left side, and if you're approaching from the right side also, when z approaches to 0, this the complex function must be same. And as well as when limit z tend to 0 minus dou f tilde by dou z must be equal to when limit z tend to 0 plus dou f tilde by dou z. So these are the boundary conditions. Okay, now we can apply this boundary condition. Now z tends to 0 minus means we are approaching from the left side. So when you approach from the left side, that is from z less than 0, and when z approaches to 0, what would happen? The left side would become ai tilde e raised to minus I omega t plus ar tilde e raised to minus I omega t equal at tilde e raised to minus I omega t. So just using this equation, so we can give some number for this. So this can be equation number 7. Okay, so by using equation number 7, we can write like this. And e raised to minus I omega t is the same throughout. So therefore, we'll get ai tilde plus ar tilde equal at tilde. This can be equation number 8. Similarly, we can find out the next boundary condition. Okay, so when limit z tends to 0 minus dou f tilde by dou z. So for that, we have to find out the first derivative with respect to z. So if you find the first derivative with respect to z, it will be ai tilde will get same e raised to I k1z minus omega t. Then I k1 would come outside, and there will be a minus sign, a r tilde e raised to I minus k1z minus omega t, this minus sign, okay, better put plus sign, then minus I k1. Okay, so there is the left side, and what about the right side? This limit z tend to 0 plus at tilde e raised to I k2z minus omega t I k2. Now put the limit then. So put the limit z tends to 0 on both sides. Then what you will get is the k1 can be taken common. So k1 times ai tilde minus ar tilde equal k2 times at tilde. This can be equation number 9. Okay, so now we have got two equation, equation number 8 and equation number 9. So it actually connects the incident amplitude, the reflected amplitude, and as well as the transmitted amplitude, basically the complex amplitudes. Now from this, by solving these two equations, we can actually find out the reflected amplitude, the reflected complex amplitude, as well as transmitted complex amplitude in terms of the incident complex amplitude. So it is very easy to find. So what you can do is just take this k1 to the right side. Okay, so equation number 9 we can write like this. Now, if you just add equation number 8 and equation number 9, what you would get? Just adding equation number 8 and equation number 9, we'll get 2 ai tilde equal 1 plus k2 by k1 a t tilde. Now this k2 by k1 we can write as v1 by v2 using this expression, equation number 6. K2 by k1 is nothing but v1 by v2. So therefore 2 ai tilde equal to 1 plus v1 by v2 a t tilde, or what would be a t tilde? So a t tilde would be 2 v2 divided by v2 plus v1 times a I tilde. So what I have got is, we have got the expression for the transmitted amplitude, the complex transmitted amplitude in terms of the incident complex amplitude. So we can put some other equation number for this, equation number 10. Now by substituting equation number 10 in any one of the equation number 8 or equation number 9, we can get the expression for the reflected amplitude. So the reflected amplitude AR tilde, it is found to be V2 minus V1. So this you can do it yourself. V2 plus V1 AI tilde. It can be equation number 11. Okay, so just by using this boundary condition, I have got the expression for the transmitted amplitude and reflected amplitude in terms of the incident amplitude. So the how much the wave is getting transmitted and how much wave is getting reflected, we can easily find out from the equation number 10 and 11. Okay, now this equation number 10 and 11 basically contains both amplitude and phase, because these are the complex amplitudes. Now we can divide into two. We can divide the amplitude part and as well as the phase part separately. So if you take equation number 10, at tilde we can write as at e raised to I delta t equal to v2 by v2 plus v1 ai e raised to I delta I. Now we can equate the real part and complex part separately. So therefore this implies the real amplitude, the real transmitted amplitude is simply 2v2 divided by v2 plus v1 times AI can be equation number 10a, and e raised to I delta t become equal to e raised to I delta I. So that means delta t must be same as delta I. It can be equation number 10b. Okay, so we have got the expression for the amplitude and phase. So we can see here that the phase of the transmitted wave and incident wave are same. So that means if the crest incident at the boundary, then the transmitted wave will start at the boundary. So if we have a boundary, if the crest is incidenting here, then the reflected wave would also start with the crest. So it will be continuous. Okay. Now what about the reflected wave? So reflected wave, we can just divide the equation number 11. Equation number 11, it is AR e raised to I delta R. Now V2 minus V1, so there are two possibilities. The one possibility can be V2 greater than V1, and the other possibility is V2 is less than V1. So better we can write it is a plus or minus modulus of V2 minus V1 divided by V2 plus V1 AI e raised to I delta I. So you have to use plus when V2 is greater than V1, and we have to use minus when V2 is less than V1. This equation. Okay. Now again, this can be divided into two parts. We can equate the real part and the complex part separately. Now the amplitude is always taken to be a positive quantity. So therefore, we can write this AR simply equal to the modulus of V2 minus V1 divided by V2 plus V1 times AI, and e raised to I delta R can be equal to plus or minus e raised to I delta I. So there are two conditions now. First is V2 is greater than V1. So if V2 greater than V1, we have to use positive. So for V2 greater than V1, e raised to I delta R simply equal to e raised to I delta I. So that means delta R equal to delta I. Okay. And the second situation is V2 is less than V1. So when V2 is less than V1, e raised to I delta R equal to minus e raised to I delta I. Now how we can equate delta R and delta I? So delta R and delta I are not equal. Now it is possible to write this minus 1 as e raised to I pi. And therefore, if you look at this, minus 1 is simply e raised to I pi. So therefore, the right side can be written as e raised to I delta I plus pi. The left side is e raised to I delta R. So finally, what you get is delta R is equal to delta I plus pi. So that means the reflected wave and the incident wave are not having the same phase. So they are having a phase difference of pi. Okay, so the reflected wave is out of phase with the incident wave if V2 is less than V1. Okay, so when you will get V2 less than V1, so the V2 less than V1 means mu2 is greater than mu1. So if the second string is thicker, if the second string is thicker, if the second string is heavier, then the reflected wave has a phase difference. There will be a phase flip. So we can call this as the phase flip for reflected wave. And if the second the string is lighter compared to the first string, then there is no phase flip. So there is this condition. If v2 is greater than v1, v2 greater than v1 means mu2 is less than mu1. So the linear mass density of the second string is lesser than the linear mass density of the first string, then delta R and delta I are same. So there are two situations now. So one is the first string is thicker and the second string is lighter. So here V2 is greater than V1. So if V2 is greater than V1, then there is no phase flip. The incident wave and the reflected wave is having the same phase. So if this is your incident wave, then the reflected wave would like, sorry, the reflected wave would like this. There is no phase flip. Now what about the opposite situation? So you have a lighter string first, then thicker string second, a boundary here, you have an incident wave, then the reflected wave will have a phase flip. There is a phase flip of pi. Okay, so that is what is meant by this phase difference. Okay, now whatever be the strings, the lighter string or upper, heavier string, the transmitted wave has no phase difference. The transmitted wave has no phase difference. Only reflected wave may have, there is a possibility of phase difference. And again, there are certain conditions. So the phase difference is possible only if the second string is thicker or second string is heavier. Okay. Now, finally, we can write the real functional form of the incident wave and reflected wave if you want. So the reflected wave, we can write Fr of Zt. It is Ar cos of minus Kz minus omega t plus delta R. Here delta R can be delta I or delta I plus pi, depending upon this condition. It is if V2 is greater than V1, delta R is equal to delta I, and if V2 is less than V1, this is the situation. And AR is modulus of V2 minus V1 divided by V2 plus V1 times AI cos of minus K1Z minus omega t plus delta R. And what about the transmitted wave? The transmitted wave Ft of Zt is 2V2 by V2 plus V1 times AI cos of K2Z minus omega t plus delta I. So we can write delta I there itself because delta I and delta t are same. So that's about the transmitted wave. Okay, now we can have a special situation. Suppose you have a string and at the boundary we have a big wall. Okay, so we know that it is not possible to the wave the propagate through the wall, so there will not be any transmission. Okay, so why it is why there is no transmission here? Because here this wall is very heavy and its mass per unit length is very large, so the V2 is almost zero. So there is no speed, there is no propagation of the wave in the second medium. Okay, so if the second medium, or if the second string is very heavy, then there is no possibility of the transmitted wave. So the V2 is almost zero. So that we can see here. So if V2 is almost zero, then what would be Ft of Zt? If V2 is zero, then Ft of Zt is zero, because At depending upon V2. Okay. So At is 2V2 by V2 plus V1. So if V2 is 0, then At would be 0 or Ft would be 0. Then what about Fr? So since V2 is 0, it is simply Ai cos of minus K1Z minus omega t plus delta R. Now delta R we can easily write as delta I plus pi, because here V2 is less than V1, because V2 is 0. V1 is not 0. V2 is 0 and V1 is non-zero. So therefore V2 is less than V1. So obviously we can write like this. So therefore, if the wave, if the string is fixed at one end, okay, so this is a situation, it is fixed at one end. Okay, so if the string is fixed at one end, then the reflected wave will always have a phase flip. So there will be an extra phase difference by here. So that means if you have an incident wave like this, then the reflected wave would be like this. There will be a phase flip, and it has the same amplitude. So both incident wave and the reflected wave will have the same amplitude AI, but there is a phase flip of pi. Okay, so that's all about the wave in a string. So we have discussed in detail about the propagation of wave in a string. We have set up its the differential equation. We also discussed how to represent the wave function in a complex notation, in a complex form. And finally, we have discussed how to utilize the boundary condition in order to find the expression for the reflected wave and transmitted wave, its amplitude, and as well as the phase relations. Okay, so that's all for the time being. So thanks for watching this video. So we'll come up with few other topics in next class. So see you soon. Bye.